Yeah, as I was planning my talk over the week, get my laptop working here, I decided to take a little bit different approach than I normally take in these climate change talks, um, mainly because of how dry it's been in a lot of places around the Northeast. So I'm gonna kind of take a climate change and drought focus and kind of play off of the recent drought conditions. And I think the thing that got me going on this was we do a good part of the drought monitoring across the Northeast, and in one of the listservs that we look at, one of our cooperators posted this, and you can pretty much, I guess, the Trout Unlimited kind of caught my eye. This is not in your area, but up in the upper Susquehanna region of Pennsylvania and New York. Um, but this drought that we've seen over the last couple of months, at least in my mind, has been unusual for a couple of reasons. And I guess the main one that comes to mind are all the fires that we've seen across the region. Definitely not a thing we normally talk about in the Northeast. And then also this kind of word here, ecological drought. I always hear that kind of bantered around and things like that in the meetings that I go to. And, I often say to myself, oh, that's a thing for the people out west to worry about and not us, that we really don't have ecological drought in the Northeast. But I think this impact on some of the streams in, again, southeastern New or, south central New York and Pennsylvania indicate that that is indeed something that can go on. And it's, again, in this case, it's not only the trout or the trout eggs, but the lower impact there. People trying to establish tree plantings in riparian zones have also run into some problems this year with those trees surviving. So, yes, it's been dry, and I guess the drought monitor gets updated each Thursday morning, and I don't have the more recent slide here, but if you kind of imagine some red here across kind of eastern and central Massachusetts, where that is, you know, that's where we get into pretty much exceptional drought conditions in that region as well. So kind of unusual here for this area. Let me minimize you guys. Your faces keep getting in my way here. All right, that's a little bit better. If we look at kind of some of the drought indicators, what I'm looking at here is an index called SPI, the Standard Precipitation Index. And really what that does is look at the current precipitation departure and sort of cast it into percentiles. So all those kind of burgundy dots across Massachusetts, both over the last 60 days and the last 90 days on your right, represent conditions where the departure of rainfall is in the lowest 2%. So you would only expect to see rainfall deficits that extreme 2 out of 100 years on average. So again, it's truly an extreme drought. I guess we also looks like there was a USGS person on the call, and we use quite a bit of their data. Um, Oops, excuse me. And this is from their streamflow network on the left and groundwater status on the right. And again, you see a lot of those deep burgundy dots across most streams in Massachusetts, indicating that they are much below normal. In the lower 10th percentile, when they're kind of this burgundy color, and these couple of bright red ones are actually beyond that, almost a record low. And to the right, you see groundwater levels across the state as well, and kind of lots of reds and oranges there indicating the lower percentiles. Not too surprising to see the groundwater kind of lag the stream flow as an indicator. There's a little bit more buffer in those groundwater levels, so not quite at the extreme when we look at groundwater. And again, just picking what I thought was a random stream in western Massachusetts, again from the USGS. Basically, the pretty colors, the browns and the blues, show the range of flows on average daily discharges on the west branch of the Westfield River. The black line shows the current flow on that river, and as you can see, it's very low in the lowest category here. Actually, if it wasn't for this one period of flow here in one of the records, if that kind of continued through, we would be almost seeing record flows, low flows in this drought. Um, so if we kind of start to get the climate change perspective and look back, I'm showing here the record from a monitoring tool that's called the U.S. Drought Monitor. The Drought Monitor only goes back to 2000. That's when it was instituted. And again, remember that Massachusetts is in this D3, this extreme drought level. And if you squint your eyes really good, there's 1 week here at the end that has that. But the point that I want to make is the state has been in, or some part of the state has been in extreme drought at least 3 other times since the drought of 2016. So over less than a 10-year period, we've seen actually four of these droughts now, which are only expected to occur, once every or twice every 100 years. So clearly a change in what we might expect for drought. If I look back to the beginning of the drought monitor, again, notice there are no reds, no D3 or D4 drought. We can take a longer look back in time with the Palmer Drought Severity Index, a bit simpler of an index, relying just on temperature and precipitation. But because of that, we can extend the record back all the way to the late 1800s. So really the way that this index works, at least for now, for this talk, is anything that's green is definitely not drought conditions. It's excessive moisture. And really where we start to get concerned about drought is when that index drops below -1. You can think of that -1 in this index as being about a standard deviation. So if you see again in the more recent period, pretty much from the 70s onward, there's a lot of green in there and really only these small interspersed droughts. If you look in the period previous to about 1975, you really see a different pattern, a lot more brown, a lot more droughtiness. And when the droughts occur, they tend to last for a longer period of time. You don't just get 1 or 2 bars together, you get nice groupings of bars. Clearly, the 60s drought stands out here quite well. But again, a several year drought here in the late 40s, early 50s, and a few back here in the early 1900s, actually. So really a change in the character of drought. We've entered a wet period. That's why you see lots of green. But these wet periods are interspersed with some droughts. And notice the 2016 drought, even though it didn't last very long, it was among one of the deepest droughts on record basically in terms of this index. It's probably, if you count these as one in the one drought, it's the third or fourth lowest, most severe deficit in rainfall. So why has this been happening? So I'm going to switch to meteorology, and this is a map of the upper air pressure. So this is air pressure going all the way back to August of this year, and it compares it to the 30-year average. Basically, anything that's blue you can think of anything that's red you can think about as a high pressure system. So really, the story here is this big honker of a high pressure system has been really sitting over the Northeast and the Midwest for the last 3 or 4 months now, and really not budging. So really, their drought conditions in our region, particularly to the south over New Jersey and Maryland and West Virginia, really started back in August. So again, when this high became established, and as the high persisted, the drought conditions kind of moved up into Massachusetts and southeastern New York. I think an interesting feature of this is kind of this bulge, this kind of notch that you see out of the high pressure system. And if you kind of notice where it is and things like that, I think we can blame that on Hurricane Helene coming in and affecting, here's western North Carolina and Tennessee and up into Virginia. So you see an indication of that. And that's also important for another reason, because kind of if you think back to this hurricane season, there were quite a few storms, but none of them really made it up into our region or made it up appreciably into our region. They were all pretty much shunted off to our south. So that's a contributing factor to the dry conditions that we see. And I think a contributing factor to kind of the unusual timing of this drought. Not too often do we see droughts become established in October and November. Um, just how dry it was. October was phenomenal. The driest month on record in many places across the Northeast. I guess if I look down at Worcester, about the fifth driest in central Massachusetts, at least the fifth driest October. These places over here, the ones up in the New York City area, are the driest month, any month. It could be August, could be July, the driest month ever. So you see that in a number of locations. And then also hone in on the precipitation amounts. In the month of October, any place in New Jersey or the New York City area essentially got zero rain. Just a trace at Newark and Philly, and less than a tenth of an inch at most places, even up into Connecticut. Um, and what we've seen lately in terms of fire weather, almost record numbers of brush fires across Massachusetts, across Connecticut, across New Jersey. And what I'm showing here is an index, sort of an index of fire weather. It's the Weather Service issues these red flag warnings. They're kind of a mix of how dry it is and how windy it is. So the numbers on this graph show how many of these warnings were issued in different months in different years. So across Massachusetts, here we are sitting in November of 2024, not even through the month, not even through the month yet. And they've issued 12 of these warnings, second only to the 13 that were issued in April of the 2012 drought. And then the other thing to notice is, boy, all of these red flag warnings are typically issued in April and May and March when we typically expect fire weather in the Northeast. Yet we see the majority of them this year being issued in the fall in October and November. So a very interesting timing of things this year. So if we kind of take a longer term perspective, kind of climate change, and I'm going to try to tie it to those parameters that affect drought. And again, to tie that kind of to the group that I'm talking about, think of this as low flows, and eventually when we talk about temperatures, the combination of lower flows with changes in precipitation, or actually we'll see higher flows and increased water temperatures. So across the state of Massachusetts, looking at data from the National Climatic Data Center. Their data go back to 1895. These are a number of stations averaged across the state. And I'm showing the 4 seasons of the year, looking at the trend in precipitation in those seasons. The kind of horizontal gray line in each of these is the very long-term average. And then the blue line is the trend through time. So I've drawn that trend through the entire period of record. Kind of the take-home message here is all seasons are seeing an increase in precipitation. The increase across Massachusetts, at least, is greatest in the fall. Basically, a quarter of an inch more precipitation during the year each decade. And then if you look at the spring and the summer and the winter, they're more on the order of a tenth of an inch of rainfall. But nonetheless, all increases in total rainfall. If we look at kind of how that plays out regionally, pretty much all counties across the Northeast are seeing this type of a trend in rainfall, annual rainfall. This is the entire year now. And these darker green areas across kind of the Catskills of New York and into southern Vermont and things like that are on average in the year about 3 inches more precipitation every decade. So, if we, average precipitation here, annual precipitation is probably about 40 to 50 inches. So we're looking at about a 10% increase per decade. If we switch gears and look at temperature, you could argue that these are pretty similar graphs in terms of the trends, just different colors, and that's probably true. So again, Massachusetts average temperature for the winter, spring, summer, and fall, long-term mean by the horizontal line, and trend indicated by the blue line. So if we pick on summer, where actually the trend is the greatest in this record, actually summer and spring, showing about a tenth of a degree, or I'm sorry, 3/10 of a degree and 4/10 of a degree change per decade. Kind of, at least in my mind, it's really interesting to look at this average and say, boy, what we would have thought of as among the highest summertime averages back in the late 1800s through about the 1940s. We now look at that, and that's among the coolest of the summers that we get. So a real change here in the summer climatology, where pretty much any summer we've seen in the last 20 or 25 years has been warmer than the warmest summers we saw earlier in the record. And I've struck a linear trend here, but actually that's not too bad of an estimate on how the temperature has changed through time. You might argue a little bit of a flattening in the middle. And we really see that in all seasons, the same type of thing. Most of the values are below the line here, and most of the values are above the line in the recent climate. So temperature has been our real changing point, or at least average temperature has been our real changing point across much of the Northeast, as we can see here on the map as well. Pretty much all counties showing a fairly substantial, in the dark red, increase in temperature per decade. Coupled with that are changes in evaporation. And I'll admit these maps are not observed, but I am kind of projecting out into the future a little bit. Should have labeled these a little bit better. But at the top, kind of the brownie type graph here, these are the expected changes in summertime potential evaporation under high emissions of CO2 into the atmosphere in the mid-century, so kind of around 2050. So really what we're saying here is by 2050, we expect evaporation, or at least potential evaporation, in the summer to be about 5 inches more than it is today. If we move out to the end of the century, that's more like 10 inches more evaporation during the summer months. So this combination of, might say, if you go back to the earlier slide, you might say, Art, well, you're telling me it's going to rain more. When you combine that with the increase in temperatures and the resulting increase in potential evaporation, basically the evaporation wins out. And that's kind of this idea of getting more frequent droughts interspersed in a wet period of time. Another thing that plays into this, and this is kind of newer research, I would say, in the climate literature. I don't think there's quite 100% consensus about this. There's still some debate in the literature, but really the story that's starting to win out is another thing to expect under changing climate conditions is for the weather to be more persistent. So going back to that slide that I had of the high that's been sitting over us since August and not moving is a good example of this. And why does weather become more persistent under climate change? Well, the thinking is kind of up here. If you look at this graph, if basically the Arctic regions are warming at a much faster rate than areas further south. So you have a lot of warming in the Arctic, still warming, but not as great of warming across the mid-latitudes in the tropics. And what that does is it decreases the equator to pole contrast in temperature. So the difference between the equator and the poles in temperature has become less through time because of this enhanced warming in the Arctic. And, how does that relate to weather persistence? Well, it's that contrast between the cold Arctic and the warmer mid-latitudes and tropics that really drive and dictate the strength of the jet stream. So the jet stream is very, very strong when that temperature contrast is is also very strong. That's kind of that contrast is the thing that really forms and determines the strength of the jet stream. And as that contrast weakens, so does the jet stream. And that does two things. It just slows down the wind speed. So you can think of it as there's not as much kind of wind pushing the weather systems from west to east as we would normally expect. So that's one ingredient in that. And the second is a weaker jet stream tends to meander more. It's not as, basically it gets lots of waves in it. And when the jet stream gets lots of waves in it, not only do those waves tend to be persistent, but those waves tend to bring us very anomalous weather, either very, very dry or very, very wet or very, very warm or very, very cold. So that kind of wavy jet stream and the fact that that jet stream position is not moving as quickly gives us this kind of more persistent weather. And kind of like I alluded to, it works for drought, it works for dry weather, but it also works for rainy periods as well. You can think of it in terms of temperature, particularly in some of the heat waves, not so much in the east, but in the last couple of years that have made the news out west. You can think about it that as many of the persistent western wildfires that we've seen, the wildfires up into Canada. That brought us the smoke a couple of years ago. All of these things are related in some way to this more persistent weather patterns. Kind of along a similar lines, again, kind of a new way that the climate literature is evolving is an area that's called attribution. And what attribution does is it basically takes an observed weather occurrence, and this is out of a paper that the researchers were from Europe. So they're looking at actually a very heavy rainfall event across Central Europe. That's indicated. The blue here is the amount of precipitation. So this storm in parts of, I don't know, what is that? Is that Austria, I guess? We're seeing somewhere around, almost 200 millimeters of rainfall. So kind of, just shy of maybe 8 inches of rain if I'm doing the conversion right off the top of my head. And then we look at that same kind of weather system simulated by a model. So you could argue with me about the details, but I would argue pretty much the model is doing a pretty good job of simulating that system. It's definitely getting the position right, and I would argue it's getting the amount of rainfall right pretty well. What we see at the bottom is, again, once we get this storm kind of portrayed in a model, we can start to play games with the model. And we could say, boy, what would this storm have looked like? This storm that occurred in the present day climate conditions, what would it have looked like if it occurred in the pre-industrial era? And that's what this map is showing. So we see our storm here across Central Europe. There's a lot of kind of purples here. So if we look at the scale here, it says the total precipitation change is about 50 millimeters. So what this is saying is in the present day era, this storm had about 50 millimeters more of rainfall than if it occurred in the pre-industrial time. So it's kind of saying, all right, out of this 200 millimeter storm that people saw, about 50 millimeters of that was due to the changing climate conditions. In the last panel, what they did was make the climate conditions a little bit worse. They upped the temperature of the Earth, the average temperature of the Earth by 4 degrees C, and ran the model. And you can see a similar pattern across Central Europe, about the same change. There's some purples in there, kind of more spread out. But also notice to either side of this storm, there's a lot of drying. The rainfall that they saw in these areas was actually less than what they saw during this storm in the present era. So again, it's an idea that under these very, very warm conditions, not only does it rain more, but the rain becomes more concentrated. It's become more spatially concentrated here. And out away from that, some areas get kind of deprived of the rainfall that they might have. So this would be another argument for how droughts and floods could go together under a changing climate. Um, an example here across the region of a big rainfall days. Yeah, an inch isn't that much, but we could show this for 2 inches or even something like the 10 or the 20-year storm, and quite consistently it would show an increase in the number of these very, very heavy rainfall days as well. 1 inch, 2 inch, or up to 5 inches and things like that. And we have definitely seen our share of that across our region over the last few years. You can look at Helene, you can look at Ida in New York City, you can look at Irene, you can probably name any one of these storms, not only tropical storms, but the weather system that affected parts of Western Connecticut and in the New York City area this year, kind of just typical summer thunderstorms with a cold front going through caused dramatic flooding and very heavy rainfall. I want to kind of jump to the future in the time that I have. Um, and I'm gonna, basically we're doing this all with climate models. Climate models aren't perfect. They are getting better through time. And really the core of what I'm going to talk about in my talk on what the future holds is really comparing results from the very latest, the most recent generation of global climate models with the version of models before that. So, basically over the last 4 or 5 years, the models have improved in how they handle some of the physics of the atmosphere, some of the feedbacks between the different systems. Computer capacity has increased, so the resolution of these models has been able to increase. So just an overall kind of betterment of the models as time has gone on. All of the models, and there's a slew of models out there. There's probably 30 or 40 models in this new suite of climate models. That's pretty typical. Different modeling groups throughout the world produce these models. They're all based on exactly the same physics. So at their core, they're all pretty much the same model. Where they differ is in kind of how they handle the things that really either can't be described well by the physics. We don't know the physics that well. Things like maybe ice sheet melt and things like that, or processes that occur at scales that are much, much smaller than the grids of the model. So grid of a current day global climate model is on the order of about 100 square kilometers. So definitely better than the, 2.5 degree resolution that may have been, that was common, not even 10 years ago. But really at those subgrid scale things, things like clouds really pop into play. Really what makes a cloud reflect radiation versus trap heat is really how small the droplets are in the cloud. So that can't be modeled because it's too small of a scale. So the modelers have to make some assumptions on how at this climate model grid scale are we going to represent the reflectivity of a cloud. And I might do it one way. Randy might choose to do it a different way. Neither one of us are right or wrong, but we're doing it differently. They're both feasible approaches. And that's one of the reasons why you'll see the differences in some of the models as that we'll talk about in a bit. Again, it's all about scale. This is a typical resolution of a climate model, at least with respect to the California coast. For going down to a Massachusetts scale or something like that to start to resolve these, we either need lots and lots more computer power or some methods to go from the GCM scale down to the local scale, which collectively is called downscaling. So what do the new models say? Kind of start off with maybe the good news. Really, the new thinking in how the climate is going to evolve is, I would say, the silver lining is in what emissions scenario people think are going to be the most likely. That may change in the coming year, but previous thought was really up on this red line here, or one of these red lines here, that was considered a high emissions scenario, where basically from, about, 2000 out to the end of the century, we're pretty much going to triple the amount of carbon dioxide that is released into the atmosphere each year. Um, since then, the thinking is probably more along these yellow and orange lines. So that's a new kind of scenario that's been brought into the modeling world to kind of reflect some of the changes, some of the commitments for reducing carbon dioxide emissions. If you kind of look at that line, it sort of peaks here at about 2040 and then in many cases starts to decline. So that's a lot of these efforts to reduce carbon dioxide emissions after 2040 or 2030. So hopefully that will be the case, but I think time will really tell to see if that's the path we take or if we're again more up in one of these higher levels. But in any way, in some of the slides that I'm going to talk about, I'm going to call the red emissions scenario very high. I'm going to call the yellow emission scenario high. And then there is a more optimistic scenario here in the gray, which I'll call low. Not going to talk about this lower one. And just if you're interested, that's if we get really, really aggressive and not only cut our emissions, but actively try to suck carbon dioxide out of the atmosphere. So would basically call that aspirational at this point. Um, that was the good news, at least that at least the modelers and the impacts people think we're on a lower emission scenario. I would say maybe the little bit worse news is collectively the newer models tend to be warmer than the older models. So if we look at, say, global temperatures, that would result from a doubling of the CO2. Um, this is the range that most of the older generation of models was showing. This is the newer generation of models. So there's a couple of outlier cold ones. Um, Interestingly, they happen to be the Russian models, but really the most of the other models are actually much warmer than in the in the older generation of models. There's a group of models up here that are called they're called the hot models. I would argue I've kind of discounted these Russian models, but some of these also are thought to be maybe a little bit out of line in terms of how warm they are. But even without those, the current models are typically higher in their temperature with a doubling of the CO2. Um, Having said that, both the models are not only run out into the future, but they're also run on the historical period. So the dark black line is the observed climate from 1800 to 2020. And then the blue and the gray lines that are kind of superimposed are the new generation of models in the blue and the older generation of models in the gray. So really, both of the models are doing equally well. No real change in how they model the historical period of time. And why that's important is even though I said the newer models tend to be warmer in the future, that is their response to an increase in CO2. They're not warmer than the older models under the current climate conditions. So it's how they're responding to the enhanced CO2 that really matters. Um, you know, kind of really, I don't want to say too much about this slide, but kind of use it as a way of introducing that really the things that are easy to model or infer from a climate model are kind of up in this upper right-hand corner of this graph. And as you go down, and particularly if you go down to the lower left, those are some types of impacts that get harder and harder and harder to kind of tease out of climate models. And I'll argue floods are fairly high. They're probably next on the list in terms of heat waves and temperature and precipitation. But droughts are pretty low on the list. It's hard to really for the models to capture large droughts for a number of reasons. The droughts are not just dependent upon the atmosphere, but many land surface characteristics, many land use characteristics come into play with drought, many local scale phenomena. And in places outside of the Northeast, particularly if we were talking about, say, the Western United States, um, droughts or longer term drought periods there tend to be tied to kind of very pronounced sea surface anomaly patterns and things like that. So, sort of like El Nino, but other patterns besides El Nino. And the models aren't all that good at reproducing this historical occurrence of those types of patterns. So it is harder to kind of pinpoint the real causes of those droughts and model them in a model. Um, so kind of looking at how things kind of play out, we use what are called an ensemble of models. So in the new generation of models, at least in the models that are forming this graph here, there's 16 of the models are averaged together, and the average of those models is shown by the solid line, the solid green line in the middle. The shading represents the range of what the models say. So the warmest, or in this case, yeah, the warmest versus the coldest model in any given year. And the dots in the background are the observed conditions. So the points to make on this are the models do a fairly good job of capturing the range of observed climate. The average of the model does a pretty good job of capturing the average over these periods of time. Um, the average of the models does a good job of capturing the trend in the observations that we've seen. And then if we go out into the future, we can see the current climate of, an average temperature, at least in Worcester County, Massachusetts, and that's an average annual temperature of something like 40, oh, we'll call it 47 or so in the current climate. By the end of the century, averages almost 57, almost a 10-degree Fahrenheit increase in that temperature. And lots of variation. The warmest models are above 60, and the coldest models are, just shy of 50 in those cases. So a fairly large range, particularly as you go out, but nonetheless, pretty much can't say that there's not warming in the series. Um, Precipitation, on the other hand, this is the exact same graph, but with precipitation, and I would argue a lot more messy. Still the models get the observations pretty well. The range of the model captures the range of the observation. The trend ain't too bad. It really doesn't exist in either the model or the observations. And then as we go out into the future, oh, you might squint your eyes and say that that does increase. Most of the line is kind of straddling 50 out at the end of the century as opposed to being below 50 here. So maybe about a 5% increase in total annual rainfall in this location, but still with quite a bit of variability. The dry years are pretty much the same, regardless of where you look. Um, would argue there's many more wet years here than there are in the bulk of the pre-industrial climate. Um, Number of big rainfall days. So here I'm looking at 2-inch rainfalls. This is likely to spike the flow on a river or a stream and things like that. Again, pretty messy. If you kind of remember that type of graph, we're getting into these ideas of really getting things like, storms or rainfall produced by hurricanes or thunderstorms that are really hard for the model to get. Um, but we do see, again, they do a pretty good job of getting the range of the observations, the average of the observations. You can see an upward trend in this as well, both in the historical and in the future period of time. So a 2-inch rainfall event in Worcester County basically occurs once per year in the observed climate. And by the time we get out to mid and late century, it's going to occur twice on average. Um, so the next group of slides, I'm going to go through them pretty quickly, but I'll give you the lay of the land first. And what I'm going to do is I'm comparing the new runs of the models. That's the Loca 2 with the older runs of the models, the Loca 1s, and I'm going to compare a bunch of different variables. So basically, what I want to say is across the Northeast, what does this new generation of models say about how the climate is going to change as opposed to what we knew 3 or 4 years ago? So this is average annual rainfall. Um, it's a pretty messy map. It looks like it's Christmas basically. And how I would interpret this is there's really not much difference in how the newer models portray precipitation across the Northeast. Um, not in the middle part of the century from 2031 to 2060 or in the later part of the century. Pretty much, they're, equally some areas are getting drier and some areas are getting wetter. Again, this isn't saying that, where I live in upstate New York is getting drier, but what it says is the new models made that area a little bit drier than the old models did. Everybody is seeing an increase in rainfall, so it's kind of superimposed on that. So really, again, hard to find a signal there, and that's really the message. Um, Now, a little bit different if I look at temperature. So I'm looking at, again, the difference in temperature from the old and the new model runs. I'm looking seasonal. So the graph on the extreme left here, or my extreme left, is the end of the century in spring. Lots and lots and lots of red across the region. If I pick on Massachusetts here, it's basically saying that the newer models show that spring temperatures are going to be an additional half to 1 degree warmer than on top of the warming that the older models say. So the newer models are saying climate change gets worse by a half to 1 degree. If I look in summer, actually quite a bit of blue. And basically what that's saying is not that summers are going to cool, but the new models are slightly cooler than the older models for summer temperatures across a good swath of the region. And then if we move into fall, the same type of thing, basically a mix of very light blues and very light reds. And I would interpret that as pretty much no difference in the model. So kind of interesting that the newer models, enhance the warming in the spring and seem to temper it a bit in the summertime. Um, what I show here is these are both the newer models, but what I'm showing is this is mid-century to the left and the end of the century in the right. And what I'm showing is the difference between two scenarios. So it's the difference between the very extreme emission scenario and the high emission scenario. So if I look at the end of the century, what it says is the difference between being on that high emission scenario that folks think we're on now versus the very high, which was the most likely case a couple of years ago. That really reduces the warming in average temperature across a good portion of the Northeast by about 3 degrees Fahrenheit. So a substantial difference there in the response. Keep in mind, in one of my earlier graphs, the warming in this area was about 10 degrees at the end of the century. So it's being tempered, but we're still talking about a good 7 degrees of warming even under that scenario. For precipitation, same type of thing between the high and the very high emission scenario. Not much difference in mid-century. If we look at the end of the century, the darker greens across the Atlantic coast are basically saying the very high emission scenario was about 2 degrees wetter. So again, that lower emissions is going to have the precipitation go down as well. And here again, what I'm looking at is an even, what am I looking at here? I forgot what this is. I made a mistake in my earlier slides. Here I was comparing very high with that kind of actually low emissions scenario. So not kind of the two extremes of the emissions scenario. And what I want to show in this one is what I said, the very high versus the more moderate one. So you can see the tempering there is not 3 or 4 degrees, but more like 1 or 2 degrees, and really makes no difference in the middle part of the century. The carbon dioxide, the effect doesn't really accumulate in the atmosphere as well. Sorry about that. And then that's that for precipitation between the two scenarios as well. So a little bit wetter in the very high as compared to the moderate as we would expect. Um, Kind of my last two slides is we do a lot of work here with very extreme rainfall, and what I'm looking at here is some work we've done for the city of New York in looking at rainfall events that are on the order of a 2 year return period out to a 100 year return period. So in New York City, a 2 year storm is, oh, probably on the order of about 4 inches per day. And a 100 year storm is probably on the order of about 8 or 10 inches a day. And again, I'm comparing the new family of models in the red to the older family of models in yellow. And so basically what this says is uh, with the old family of models, um, by the end of the century, we would expect these very extreme rainfall events to increase by about 15 to 20%. That yellow line is pretty straight across at about 15%. But in the newer models, particularly out here for these higher storms, we almost see a doubling. Now, a 100 year storm is not 15%, but it's about 30% higher than the current day storm. So this has some pretty big implications. At least the city is concerned for urban flooding and things like that. This is definitely some work that followed Ida in their response to Ida. But clearly, storms of these magnitudes have the same type of impact in small streams with flash flooding and things like that. And also notice if you're interested in what the dotted lines are, there are confidence interval about those old projections. So the new projections are even, for the most part, outside of the confidence interval of the error bands of the older models. Um, and that was my last slide. So I'm sure you guys have some questions. So I assume, I think Randy said the plan was to open it up for a question or two.
Thanks, Art. Um, I'll just make a comment and then we'll call on Neil. The comment is that when we often think about the Deerfield as being in Massachusetts because that's the part of the Deerfield that our activities are centered upon. But the headwaters of the Deerfield primarily are in Vermont. So in some of the precipitation uh, slides that you showed, southern Vermont looked a lot different than the part of Massachusetts that we're in, the part that the Deerfield's in. I just want to point that out to people if they're, you know, kind of breathing a sigh of relief because maybe we won't get those big precipitation events that you're predicting. Um, I think
Yeah, unfortunately, I don't think that is the case. I mean, a lot of cases with these, with these maps and these types of projections, at the scale between, Massachusetts and southern Vermont, that pretty much the grids of the models are kind of on that scale. So you really, even though you might downscale it to more local type things, you really don't get much more added information out of that. So kind of have to kind of blend a lot of these patterns with your eyes when you look at them. So I can't imagine any reason why southern Vermont would be much different at all than most of western Massachusetts.
thanks. Neil, did you have something you wanted to say?
Well, I didn't have a question, but I just wanted to say thanks a lot, Art. This was excellent. Lots
Thank
of
you, Neil.
good information, lots of various aspects looked at in different ways. And I'll just add that, as all of us here are interested in conservation, cold water fisheries, and just the inevitable temperature increases, under any reasonable expectations are very sobering when, you think of the small tributaries that go up and down very rapidly with, the available moisture and the temperature, just the temperature increase and the impacts that's going to have really, I have to say it's all the more motivating for any sort of adaptation work we can do.
Yeah, I always I don't know if cringe is the right word, but I'll say cringe when I speak to groups like this because I know stream temperature is really the parameter that they're most interested in. And boy, I have not seen much, if anything, in the literature that really talks about that, that really projects it well. There's so much on the local landscape that affects that. So, kind of have to, use the kind of infer what's going on based on the temperatures and like you say the changes in stream flow there are going to be are going to drive it quite a bit. I know in New York, the other factor of that is what might happen on the landscape with different things. So I know a lot of the Adirondack streams are cool because they're shaded by the hemlocks, and they're worried about the hemlocks and things like hemlock woolly adulgid, so the species that are invasive to the region and are basically coming up here because it doesn't get cold enough in the winter anymore and they're able to survive. So, yeah, a lot of complexity there, not only in the large scale climate, but in the local features and how the climate impacts that.
Hey, Art, it's Randy. Can you lean to your right so everybody can get a shot of the logo of one of the
You see the
greatest land
Rutgers
grant
logo
schools in
behind
the
that? Yep.
U.S.? Yeah. Rutgers, Red Team Raw. Go Scarlet Knights.
I brought the laptop up here just for that reason, Randy. I was trying to see if you noticed.
That's why I love you, buddy.
Uh-huh.
I think everybody can see why after an hour and 20 minutes of being in class with Art, you're like, it's over? Really? There's not more?
I don't know if my students will say that in the morning, but
Hey, Art, I have a question.
hi, Ellen.
Hi. I recently went to a presentation, and the speaker was talking about how the Northeast is experiencing more extreme weather compared to the rest of the country, and that Massachusetts was probably the most extreme differences in the Northeast. First of all, is that true? And second of all, what's driving that?
Um, Um, I'm trying to think how I'm going to answer that. I think it's how you define extreme. So I think a lot of that is, I don't know if I would say the Northeast is experiencing any more extreme weather than other parts of the country. I think it depends on how you define extreme. I mean, if you look at the West Coast, the heat dome that they endured, that was pretty extreme. The wildfire seasons that they endured a couple of years ago, that was pretty extreme. Some of the flooding from the atmospheric rivers, just you don't have to. I mean, just this week, the storm that hit the Pacific Northwest, that was pretty extreme. So I think the country as a whole is seeing their share of extreme weather. And why are they seeing their share of extreme weather? I think it's a number of factors, and a lot of those factors can be tied to climate change. If I look at the Northeast, I would say most of our extreme weather has been precipitation related, floods, basically heavy rainfall events. Um, you might even argue in recent years along the East Coast, heavy snowfall events. And, why is that? It's because the atmosphere is warmer. The atmosphere can hold more water vapor. And that water vapor, the oceans are warmer, and therefore more water vapor can evaporate into the atmosphere. That atmosphere can hold more water vapor. So if you think about it as the atmosphere just being a bigger bucket and more water being in that bucket, and when the bottom falls out of the bucket, when there's inevitably a storm or something like that, we get a lot of rain. And be it a hurricane, be it a winter storm, be it a summertime thunderstorm, all of those things come together. The other thing to go back on is this idea of weather becoming more persistent with time. So that's, that would be the culprit of with a lot of your heat waves that you might see in the West. We've been very lucky here in the East that we have not had the heat wave. There's no reason why we couldn't have those same conditions. It's just something that we haven't seen. And to be quite honest with you, it'll be, I don't know if interesting is the right word, to see how well prepared we are for a strong heat wave of the magnitude that they had out West. I know the cities are preparing for that, but they really haven't been tested. So that idea of kind of, getting into these persistent weather patterns plays into that, be it heat, be it drought, um, be it a hurricane season where all the hurricanes are shunted along the Gulf Coast and in areas in Florida in the southeast are getting hit by, one storm after another and there's no capacity to hold that water in the soil.
I have a question. Um, it's my perception that in like the last decade that it seems like we just have more wind, like more windy days. And I'm wondering if that is that just my perception,
I'm,
or it just seems like we got a lot more wind, period. And I
I'm
was wondering if
laughing.
that's a thing or
Yeah.
what.
I'm laughing because Randy probably knows why I'm laughing because the guy that runs our Thursday morning turf call, he could have planted that question in you because he asked the same thing. And boy, I've looked in any number of different data sets in any number of different ways, and I just can't find the data to support that. I've had students look
Interesting.
at it and things like that, because I hear that from a number of people. Boy, like I told Randy Frank, who we meet with every Thursday morning. My dad, before he passed away, he would always say, "Oh God, it was so windy today. It's getting windier." But um, just can't come up with seeing that in the data, nor can I come up with a good reason why that might be happening in a changing climate. So I guess I'm punting on that, Chris, but boy, you're not the first one to ask me that
All
question.
right. Well, there must be some of us that are
There's
feeling and
got to
seeing
be
the same
something.
thing. Then I'll take comfort in that,
All right.
or discomfort as it may.
Any other questions for Art? By the way, Ellen, thanks for joining us. You slipped under the radar.
And I'm going to put a plug in for Ben's stream photos. Those have been really helpful in our drought monitoring efforts. So, and extreme rainfall too. So, um, really neat USGS project there.
Hey, Art, every time we have our last call, the end of the season, like today, I always dread the period of time that I go through withdrawals of no Thursday morning with you and Frank and the gang. And I'm pretty sure that my withdrawals will be much later this year after having you on tonight.
Yep. Oh, that's good, Randy. That's good.
Get
Yeah,
all shaky and nervous. Next Thursday morning, I'm usually all shaky and nervous, and you know, it's part of my week.
my shaky's usually Wednesday night where I say, "Oh crap, it's the call tomorrow morning," and I didn't look at anything.
And of course, you probably think Frank Rossi's going to ask me this. Boy, I got to make something up.
Yeah.
Well, I want to thank you, Art, for taking the time to come out and over Zoom
Yeah.
and doing all the work to put in, really focusing on Massachusetts. Well, we appreciate it. Uh, it's very interesting to see the precision changing in the models. I'm sure that as we go further in this and and hopefully more and more focus gets placed upon it. We're getting better and better, more precise and more precise. And we're doing our part to try to document what we can on the Deerfield. We're participating in Ben's Flow Photo Explorer and a few of the other apps that he's put out there. So it's exciting to see those things evolve, and we're just bringing as much technology as we can to bear on being able to understand, predict, and tease out. One thing that I'll just mention that we're excited about is building capacity for being able to determine how much of an influence groundwater has on some of the streams that we're the groundwater temperature not responding to, hopefully as much anyway, to climate change.
Yeah, I know that's been the case in some of the Adirondack rivers where it has been the groundwater springs that have kind of, at least now, have been a saving grace, but hopefully that continues.
But thanks so much for doing the presentation once again, and it's great to have you on board. It's great to have all the people from who joined us from the national climate change work group. Thanks for being here.
Hey, Eric, for our March meeting, we're going to have Jen Fair, who works with Ben, and she's a hydrologist. I'm going to make sure that I let Art know when that is so he can come in and
Absolutely
listen to Jen.
Be interesting to sit in on that. Yep.
Very good.
All right,
All
everyone.
right.
Have a good Thanksgiving.
Happy Thanksgiving. Great to see you all.
Bye-bye.
Thanks, Art.
Take care, Randy.